Yeah. So, oh, okay. Then I have to open a new one. Questions?
It will work for multiple distribution, multiple colors, more than 2 colors.
Absolutely. Even infinite. Infinite.
But infinite, I guess it's.
No, basically you can say that that distribution is going to be a mixture of infinite number of colors. Yeah. Okay. Then in the next module, I'll directly go to EA. Yeah. Okay. EA. Okay. Now, with that in mind, I'm going to tell VAE, get into VAE, our first module. But we have to talk about its ancestor, autoencoder, and we will start with the motivation of autoencoder. The way we are designed, original purpose we design autoencoder is to compress the data. So by data compression, we want to represent a high dimensional data X, like in a 4,000 dimensional space, with lower dimensions, like in 128 dimensional space, right? That's called data compression. And then from this 128 dimension, I want to reconstruct the 4,000 dimension data. Recall, there are some classic signal processing way to do data compression. The first one we want to honor is PCA. PCA is saying, hey, given all these data you give me, I can find some eigenvector. And the largest eigenvector along that dimension, the data will have the highest variance. Or you can say, in 2D, in this 2D axis, if my data lies in 2D, you can find one vector that can best explain the data. And this is called E1, right? And then we have a second eigenvector perpendicular to that E2. And then, let's make sure, people more or less know PCA, right? You have this 2D data. You want to store this 2D data in the minimum amount of memory, or in 1D, right? So if you want to minimize the amount of memory, if you store all the data, then if there are, let's say, 10 data points, and each of them is 2 dimensions, you need 20 units of memory, right? But what you can do is you can find the direction, this axis, and project all the data along that direction, and then only store the distance along that direction for each data point. Right? So this data point, the last one, will be this much. So you store only one unit, one scalar value. So now you have 10 times 1, which is 10 memory units. This is a form of compression. Of course, is it lossless or lossy? Lossy, right? You sacrifice something, right? And you sacrifice the projection of this point to the orthogonal axis of this point. That's what it's saying. But compression is a way of reducing data. Compression is also a way of learning rules. Let's talk. Yes, and then this linear, this compression we call the linear projection, right? So to compress data X to Z, we times it with a linear matrix U. This U in this case is U transpose is 1 by 2. So you can just times U transpose with X, and then you will get a 1D Z data. How do we reconstruct X from Z? You again times U inverse. So X equals U times Z, and U will be 2 by 1. And now you can put this 1 and then put all these projection points back to the 2D space, and that's the compression. If we write PCA, if we visualize PCA in the encoder and decoder framework, it will look like this. The axis high dimensional, right? And then we pass it through an encoder, and then it gives us a Z space in low dimension, in this case 1D. So we only remember in Z, it only stores the scalar along this eigenvector. But how will I know which eigenvector I store? This is learned in the encoder and decoder. Encoder and decoder will remember that how to do the projection, and the projection will describe the eigenvector. So in the decoder, you will know, oh, okay, I need this eigenvector. I put it back to a 2D space, and then from the scalar, I know how far I should walk from the origin of this eigenvector. And then that comes up the reconstruction. Then I got back to the high dimensional space again. And again, this is lossy. because you lost all the projection matrices. Let's make sure we get this totally right. Everything will depend on this. Any questions?
So the reconstruction you're getting, you're losing, you're still in lossy, right?
Yeah, still lossy. You can see that in reconstruction, all the data points are along the eigenvector. Unlike the original data space, it's scattered.
So then the images that you'll get out there will be limited.
Yes. Yes. But you can ask the question, what single dimension can you learn in this data that will minimize the lossiness of? Yes. Yes, question.
So this dimension, right? So in this case, it's 2D. So the only option is multiple, right? So then in large dimension spaces, so is the latent space dimension K comes hyperparameter that you
Absolutely.
and then you retrain the network.
Absolutely. Yes. Absolutely. Yeah. In a real setting, this space will be how many dimensions? 4,000. 4,000. This space people typically choose 128, 256. Based on how many GPU you have, how much memory you have. Yes. You choose that space, and you're essentially saying, learn the rules of the data in 128 dimensional space. Okay. And then the decoder takes the points on this latent space and converts it back.
And so the smaller the number of dimensions, you could make an assumption that the loss. Yes. 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 But then, so how do you think about it, right? When you think about the scale, size of K.
It's an art. It's an art.
Okay.
But you can overtrain, right? You need to get the right dimension.
Right. So one thing you can do is if you use 2 dimensions, your loss is going to be very high. So when you reconstruct, that image is not going to look like the data that you input to the whole network.
If you use 2 dimensions, your loss is high or low. Because you get
Loss is very high. Right?
No, if X is 4,000 dimension, that's what
X is 4,000, 3 is 2 dimensions.
Yeah.
You cannot explain the 4,000 dimensional data with 2 dimensions of roots. That's too much. That you can. And there are things called network architecture search, which is an aspect of neural network design, where you say, I'm going to try to figure out what is the right dimension for Z. So it's a search on the hyperparameters. Let's forget that for now.
There was you can overfit, so you don't want to have 2,000. You want to have something. So it's not just the number of GPUs. There is something intrinsic in the problem which you have to.
True. You can optimize over this network. That means you're optimizing over the network architecture. But you cannot say my network has 10 layers, these many depths. You cannot say that. You have to optimize over that as well. That's network architecture. Okay. Oh, sorry.
In this whole example, your input's 2 dimensions and you're representing a single dimension.
Yes.
And then
Yes. Okay. Now we are asking, well, this reconstruction is lossy, right? Can we do better than linear compression? Recall, in this case, our encoder is just a 1x2 matrix, right? So that's why it can only learn 1 line. If now I'm asking a question, instead of increasing the latent dimension, I don't want to increase the latent dimension, but I'm saying, hey, I can make a little bit more complex encoder and decoder. What will I do? Or if I allow this encoder decoder to be a neural network, and this becomes autoencoder. Okay, so the same, you can see X is 2-dimensional, Z is still 1-dimensional. Reconstruction error, reconstruction data still back to 2D. Now we are saying the encoder, from the power of neural network, we can learn the curve. So you can see we learn a curve on 1D. So this is still 1 dimension because why? Because you can walk on this line. You can see that this is not a surface. This is still a line. Just that this curve goes through the 2D space. Again, if our encoder and decoder both can learn this curve, then when we project my data onto this strange curve, you can see very, very low reconstruction loss. Why? Because all these data lies in, let's call this a manifold, low dimensional manifold, this curve, right? And then what is C? C is how much I need to walk on this curve. So this data is saying that, hey, I need to walk 1.5 distance on the curve. So, okay, the decoder will say, okay, I have this curve. I start from the origin, I walk 1.5 meter, and then I get into the dimension. I now put this curve onto that. I got the reconstructed data. And this is what autoencoder is doing. And that's why it can achieve a low reconstruction loss. Because it finds a manifold, although it's 1D, it's getting through all the training data. And now we have a good compression, right? Because we still compress from 2D to 1D, but low reconstruction loss. Questions? Yes.
Basically, you have a parameterized curve. The parameters are the latent space, and the curve itself, function of the curve itself is determined by the decoder.
Exactly, exactly. Okay, so now we know what's the structure of encoder decoder. But there's one problem. Recall, we are saying that autoencoder just guarantees that the reconstruction loss is low. And actually, if you know a little bit about autoencoder, that's how its loss function is. The loss function is just a reconstruction loss. So it can do any mapping as long as the reconstruction is good. What do I mean any mapping? Means that it can map this point to here. And it can map this point to a far away. As long as this mapping is remembered by encoder and decoder. Encoder says that, hey, I define the distance, this such distance as 1. But I define as this small distance as 3. As long as encoder and decoder agree with this mapping, it knows, okay, 1 means far away, 3 means very little. That agree by encoder and decoder. Encoder will say, oh, okay. Decoder will say, okay, I now read 3, so I should walk only a small distance. And that's what autoencoder is going to do. But so in this case, it's good for compression, right? Because the reconstruction loss is low. But the problem is it's not good when we want to generate new samples from the latent space. If we want to give you some data in the latent space, it's not guaranteed that it will generate a good data. Why? Because ideally, let's say, what's the ideal generation? Ideal generation is if I take some Z here, and then the decoder of it goes back to here on the data manifold. This is in training data. Ideally, we want, if we just move a little bit from the Z in training data, it should not move too far away from the training sample images. So decoder of Zi plus some epsilon should be your training data plus some epsilon, which epsilon function, which is bounded. But this is not guaranteed by autoencoder. That means if you just move a little bit in your rule set, you can generate a completely different image, or even a garbage image, or even like an ice up and down. And that's the motivation we are going into VAE. So make it clear why this makes sense to you.
Let's say we have to
when you mix and match encoders and decoders, you cannot. You have to train the encoders and decoders together. Because whatever C space this guy is going to project to, the decoder has to learn to decode from that C space. I hope this is clear. Encoder is mapping a high dimension to a lower dimension. Hopefully these are rules. And decoder is mapping from lower to high dimensions. But the problem is, what is the problem with this? The high level summary. The problem?
I want to thank you, but then we need a lot of factor for the decoder and despite such kind of rules.
Right. But let's say we have the parameters. Let's say we have the memory and the GPU. Is there any other problem?
Any error would be very much off. Any error very much off the chart.
This, how do you train this guy? You said, hey, encoder, decoder. I give you an image of a cat. You design some rule space, it's up to you. And then you decode from that rule space, it better be exactly a cat. Right? That's the constraint we have given to the encoder. That constraint does not mean you can generate new data. Why? Because imagine, sorry, yeah. Imagine this is the point of that cat. Right? The decoder takes this point and generates the exact cat. Very good. It says, you asked me to do this, I've done solved the problem for you. But generative models want to generate new cats, right? So which means generative models want to say, if I sample some other points nearby, right? Near this was the rule for cats. I want to sample some other rules near the cat. Right? I should also get a cat. So if this was a white cat, a nearby point should give me a white and gray cat. That's what I want. But if I want that, I never specified that to the encoder decoder. All I told the encoder decoder is your input image and your output image should match. An encoder decoder has some way, has learned some rules in which there is no continuity. This point goes to a cat. The next point can go to a garbage. Yes. Yeah.
Modeling the sound, those things seems like there's something in the model that we have. They're not keeping the same.
Sorry. The
modeling part and the sampling part are not adhering to the same group. So effectively we have the only restriction is you are reconstructing. Whatever.
So absolutely. So autoencoders are not good generative models.
Exactly.
Because you never even asked the model to generate.
But effectively, by not having constraints in the neighborhood.
Yes, yes, good. So VAE will have some, that's why we put VAE as you have some constraint on your neighborhood.
What is this model good for, guys? Compression. Lossless compression. Very low, very little loss compression. Great for that. Not good for generating.
Okay. I just want to expand, I think, one of your questions, which is like, hey, encoder and decoder, how are they going to learn such strange mapping, right? The answer is, hey, think of this. If you have only one layer of neural network, maybe they will not do such strange mapping. But then your curvature, you will not be able to learn such a strange metaphor. So it all depends on how many parameters you are going to put in your autoencoder. And it's very hard for you to say, hey, I give you 10,000 parameters. You put all these 10,000 parameters to only learn this manifold, but not this mapping. You cannot do that because autoencoder, you only have one loss. He will do whatever he thinks maps the lossy function. So think of this: if you do a PCA linear compression, your encoder do not have the complexity to do such a strange mapping, this red arrow mapping. So PCA actually can be a generator, just that it's very loosely generated. Autoencoder cannot be a generator. Why? Because as long as it comes lossless, it will do some mapping, make its latent dimension semantically discontinuous. Now let's, oh yes.
Can I just follow up on this? So I think the objective of this autoencoder is compression is to reduce the storage you need.
Yes.
But does this mean like you actually need much more storage for the parameters from this one?
Yes, yes. So I mean, nowadays autoencoder they have some space for like thousands to 10,000s of space you need to store in your encoder and decoder. But hopefully your image dataset is much larger than that. So your image dataset might be gigabyte. So you don't care about this 1,000 or 10,000 parameters. Yeah. So let's visualize this. If we are looking into moon phases, so autoencoder is saying that I guarantee whatever you give me in the latent space, in the image space, get into a latent, 1D latent, I will decode it. Sorry, this one should be in this shape. on the right, the other side.
Let me just say, imagine all your pictures are these moon phases. These are all the pictures that you have. Okay? You're trying to learn some rule that will describe those pictures. Okay? And if you have this rule ZA for the image A and ZB for image B, what is the goal of generative model? The goal of generative model is if I take this point and if I give it to the decoder, what should it give me? Something between these two images. That's my goal. If you use an autoencoder, you give this point. What will it give you? Junk. May or may not. Exactly. May or may not.
Yeah.
So the question, sorry.
Yeah, so, yeah, sorry, no, that's fine. So autoencoder says that if you sample something between, it will give you some garbage, no guarantees, okay? Now, that motivates the VAE, variational autoencoder. But before I told you how VAE is implemented, do you have any thoughts on how to make? So we still want this encoder decoder structure, how to make the latent space semantically meaningful or semantically continuous.
Maybe we should pause and think a little bit. This is the second most beautiful idea in generative models. What do you have to do? What can you do? Something simple that makes sampling at this location, which is halfway between CB and CC. You sample over here, it will give you the halfway image between beams. I want to do something that will make that happen. 10 seconds of thoughts. One idea is, I take these two images and I create a new image and I put it in my data set, and that will create maybe half CB plus ZC by 2, right? That's called data augmentation. I create new images, but you can only do so much of that, right? Because this is like infinite possible images. You cannot create every possible image. Add noise. Okay? So if you add noise to this data, right, what will happen? Different noisy versions of the data might get mapped to something else. Right? There's no reason why B dash will get mapped close to ZB. It might get mapped to somewhere else. You have to say that images that are close by will map to close by points in C. How do you do that?
But actually, that's a very good thought. Right, this is a very good thought. So adding actually some variants of autoencoder also can do this thing. So for example, let's say image B, you add some noise to that and ask the decoder to reconstruct to the clear image of B, so non-added version. My input is noisy, but I ask you to denoise it, and that will give you some continuous in latent space. It's very close, already very close to VAE. Later we will see in image space you add noise, and latent in VAE saying in latent space you add some noise. Yes. Okay, so let's get into VAE. VAE is saying, hey, so we will approach VAE in two ways. The first is a more intuitive way or picture way, that is autoencoder plus some probabilistic. And the second thing is, I have promised you, we will look at VAE into using neural network to model the expectation maximization, right, on the right hand side. So let's look at the picture here first. We are saying instead of making one-to-one mapping, like encoder, mapping one image to one latent, I add some noise to my latent so that for each image, I encode it into a probabilistic, meaning that this image corresponds to a latent of a small distribution, center and the original latent space, but it has some variance. So you can add some small noises to that latent. So, and because the teaser is that because these distributions overlap with each other, this overlap creates the semantic continuity of variational autoencoder, and we will see why.
So, the original sort of question you asked is, I have these two similar phases of the moon, and I want them to map to same close points of the retina. Yeah. How do you still didn't solve for that problem by adding the noise, right? Because you could, the first phase of the moon can be on the left side of the line, but the second phase of the moon can jump all the way to the right.
Yes, yes,
In
yes.
that case, regardless of the distribution you add, you're not really bringing that.
Hold on for 2 more.
Yeah. We will see that making a distribution will also solve the latent permutation problem. We will see that making a distribution, this overlap will also solve the latent permutation problem. Okay, let's first see how variational autoencoder is going to do. So we make the encoder output the probabilistic distribution. So for example, if this distribution is a Gaussian, the encoder, instead of output a vector C, it will output two things. First is the mean vector, and also the covariance matrix sigma I. So my decoder, how do we decode? It samples from this Gaussian. It samples from the distribution Gaussian that encoder defined. So it samples from a Gaussian, which means is decoder's output, and variance is also decoder's output. And now the reconstruction loss is that I sample from the encoder, and then I decode it and compare it with my original image. This is the reconstruction output. This is the reconstruction loss. And because there are distribution overlap, so if D, let's look at this point, C and D. Okay, if I sample at this point, a decoder got sampled at this point, it might be because the original image is from C, and I got this latent distribution, and I sample here. Might also because the original image is D, I come to this distribution, the right distribution, and then I sample here. The decoder will not know. You only see the sample. But the reconstruction loss will tell. Why? Because if it comes from C, here you need to compare it with this moon phase. It comes from D, you need to compare it with this moon phase. The decoder will say, hey, what can I do? You give me the same sample, you give me a sample in between. You ask me to match either of them, right? Decoder only gets one sample, but later reconstruction loss, you are challenging it with two of them. All it can do is to generate something in between. Something in between, and that's exactly what we want.
The most difficult thing to convey in terms of all the ideas they were talking about. This is the hardest one to convey. So let's make sure we get the information.
Each input example maps to separate distribution.
Correct.
Yes, each input match to their corresponding distribution. Once these distribution overlap, and that will overlap, right? Because Gaussian, if you think of Gaussian, actually Gaussian is an infinite support distribution. So Gaussians will overlap. And once it overlaps, if you select samples, that belongs to both of the distribution. Decoder can only generate, or you need to generate something in between to minimize the loss.
Let's take it one step at a time. You have one picture. All this while we were mapping it to one point in the root space, right? And we were using the reconstruction of it. We were trying to reconstruct the same picture, right? Now we are saying, you take that picture, you map it to a distribution, correct? You sample from those distribution, many samples from that distribution. All of them should map it back to the same picture. What happens to the latent space? So which means the latent space is adding noise, but all of those noise, you're basically decoding it back to the same picture. So the latent space has to learn what rule should I learn so that if I go along that rule, the picture doesn't change too much. Does that make sense? Image of a moon. I come to a latent space, which is a distribution. I sample different points of the distribution. I give it to the decoder and I say, for every sample, you have to create the same moon. If the decoder says this point goes to some other picture, that point goes to some other picture, the loss would be very high. The decoder has to say, oh, all these points, they all should go to the same moon. Which means I need a rule in which nearby points still go to the same image. So the rule now might be, oh, change the moon phase, that black part a little bit along that axis. Because if you change that black part a little bit, right? If the rule is, what fraction of the yellow image is this black part? Let's say that's the rule. And as you go along that direction, more and more part of the image is black. Right? So now if you map this image to here, and then you sample from these points, if the decoder and the encoder learns that the point over here increases this black part a little bit, the point far away increases the black part a little bit more, that reduces the loss, the reconstruction loss.
Yes, I see our questions, yes. That's fine, very good.
So maybe just to repeat, so one thing I could do is if I have two Gaussians, I can take like with the EM, I can take the higher one, and then I can get C or D. The other thing I can do, I can run a sample, and depending on the sample, I can get C or D depending on the sample. But what you're saying, you're doing neither of those. You're taking those and mixing them proportional to probability, because I will have infinite number of Gaussian, right? Some higher, some lower. So you're saying I get multiple pictures, and I'll cross over that with the probability, and that's going to be the lowest yields, right? Rather than doing any of the previous ones.
Yes, right. Now, the only thing I would say is that not the closest VAE loss here is still reconstruction. It's just that I'm not reconstructing from one point, I'm reconstructing from samples of that conditional distribution.
You're saying the closest is the reconstruction.
Sorry.
What is the reconstruction?
Ultimately, how will you train it? Decoder will take a point which is a sample from the Gaussian, and it will create an image. And you are going to say, VAE, you didn't learn it well, because the reconstructed image does not match the original image. Right? So VAE is saying, hey, you're doing a hard job. You're giving me different points from the Gaussian, and you ask me to decode the same image. And we're saying, exactly, figure out the rule on which you can do that. And that rule will happen to be continuous, meaning as you go along the z-axis, the moon will become darker and darker and darker.
Yes. So basically, you're requiring local continuity as
Local continuity,
yes, in your data.
exactly.
And because of this, and if some data points are essentially close to each other, you're basically learning a continuous cycle across all these points.
Yes,
And if you have, say, moons and suns, and they are very, very different, so they will be continuous in their own portions.
Own portions, yes.
You are like together. What does that mean that in order to get the best loss ever, the encoder would learn to make the data points very far apart from each other so that you don't get to.
But if you pick them very far apart from each other, the decoder will the decoder will have easier time.
Yeah. We will see how we address that in the next slide. Yeah, but yeah,
So not good.
Yeah.
You see, exactly, that's a very good point.
Yeah, that's a very good point. But I just want to address previous raised question, which is how does this continuity solve the permutation problem? Actually, Raman has partly answered that, right? Because permutation says you have to order your image on a latent space in order, right? So if you put the black moon distribution, this distribution next to your full moon, when they overlap, well, the decoder will have a hard time to dealing with that because he has two very different images. And then when the sample come from their overlap, what can he do? He can only average over these two very different images, and that will incur a very high loss. So when these distribution got some overlaps, the encoder will tend to order the images in their similarity, as Daniel just said, you order moon together, you order some together. Now,
Just a couple of questions. In the previous slide?
Yes.
The reconstruction cost.
Yeah.
So the small d, what is that function?
the distance, You can think of MLE, MSE, mean square error.
Okay, got it.
Yeah.
Between the two.
Yeah, yeah, yeah.
And Q phi is the right distribution.
Is the distribution?
Is the
over
distribution.
It's the distribution that encode the output.
there. That's the posterior.
Okay.
So last one. So what did VAE do? Instead of mapping to a point, it mapped to a distribution. Sampled from the distribution and asked the decoder to reconstruct that same image. You have got semantic meaning in your root space. Beautiful, right? How do you give semantic meaning to numbers, vectors, n-dimensional space? Such a simple idea. Now, if you go along that red direction, your moon is going to become blacker and blacker and blacker and blacker. Hey, that's semantic meaning, right? You're like kind of understanding the phase of the moon. Beautiful.
Question about semantic space at this depth, but we're modeling it as a picture of distributions, and we're not doing it on every or in the info. Why the mapping in the middle of the other?
Oh, I see. So what? So what? The question is, why do you have to have this Z space at the end of the encoder? Why not do many Z spaces after every layer? That's exactly the gateway to the future. We are going to have hierarchical Z spaces coming up. Post lunch, if you decide to come back.
Yeah. So now, yeah, sorry, yeah, but okay. So the thing is that, but this kind of distribution actually hurts the reconstruction. As per question raised, the encoder will tend to do this. Hey, you ask me to output a distribution, but I can output a distribution that never overlap, which means each of the distribution is of small variance or their mean are far apart. In this case, decoder has an easy job. It's very easy. It's very similar to autoencoder again, right? Because as long as I see this sample, I know exactly which image I should map it to. So, but if encoder do this, then again, our semantic latent space does not have semantic.
Exactly. Right? This is not going to give you semantic continuity. It's only the overlap of the distributions that was giving you that.
So how do we force the encoder to output the distribution that is overlapped?
Yeah, so let's ask that question. How do we force the VAE such that these distributions overlap with each other? We want overlap, right? How do we force that? You have to change the objective.
Exactly.
Give me an example objective. Basically, in English language, we are saying, hey, encoder, you have to not only do you have to give me a distribution, but the distributions that we generate for each of the pictures, they should overlap. How do you say that mathematically?
Yeah. So in the interest of time, I will directly give you the answer. The answer is we will match all this distribution to a prior. And this prior is predefined. And in most of the case, we say it's a isotropic Gaussian. Isotropic Gaussian. So this green. Isotropic Gaussian means a Gaussian of mean zero and identity covariance matrix. And why will it give us such an overlap? So why will it guarantee an overlap? Because if you need to fit all the these aggregated posterior with this green curve, that means, hey, I have to insert a lot of small distribution under this big umbrella, so they cannot be too far away. Not only that, I ask you to fit this Gaussian. So each of these small distribution has to diverge somehow, so that there's no much holes that otherwise it will not look like the aggregate of them will not look like a Gaussian. So it guarantees that first, your small distribution are close together. Second, each of the distribution is diverse, or your variance will be high enough such that the total or the aggregate of all these small distribution will fit a big prior. Yes.
So do you need equal samples across like dogs, cats, so on and so forth?
Yeah. So Yeah, so the question is, do I need some diversity in my training data set? For example, if my training data is all cats, the answer is then your latent space will only belongs to cat. If you have two classes like cat and dogs, then the encoder is not guaranteed. I mean, in this prior laws, they are not guaranteed to make cats together and dogs together. That is enforced by the reconstruction laws. Recall, as long as they have overlap, decoder will say, hey, you cannot put cat image and dog images together. Because if I sample one thing in between, then I will have a bad job. So that is enforced by reconstruction laws. Sorry?
There are no labels, right? So that means that.
Yeah, there are no labels.
The equivalent label is some category that might be, for example, people from North America, or it would be.
100%.
Yeah.
So you see, right? Let me just say one more thing. Each image has a small mountain. You are saying bring all these small mountains under one mountain, right? That's what you're saying. If you have imbalanced data, lots of cats, very few dogs, very few birds, then what will happen is that the cat distribution, right, will come to the center of the mountain, and the other distributions will go to the sides of the mountain. Because if you think of aggregated expectation reconstruction loss, your reconstruction loss will be minimized if you reconstruct the cats properly.
So we need the balance state.
If you don't have a balanced data set, when you generate data, you're going to generate more cats because your cat mountain is underneath the big mountain. Because remember, guys, at the end, when everything is done, what are you going to do? You're going to take this latent space away with you. You're going to forget all the data. Just take the latent space and sample as a Gaussian from that latent space. Basically, you're sampling from this green big mountain. But because the green big mountain is learned in a way that points underneath it has the data rules of the real data, samples from this green mountain, when you decode, you get real images. Remember, we're going to forget all these small mountains, because all these small mountains only came because of the image. Right? To remember these mountains, you have to remember the image, because the mountain is what the encoder learned. Eventually, you only take the green mountain and use that as your generation. I don't know if that's clear, but
We will come to that actually. Okay, so a quick thing is that how do we compare the blue mountain with green mountain? Here I'm going to tell you VAE is introducing the KL divergence between two distributions, KL divergence. So PZ given X is this blue mountain, the posterior, aggregated posterior. Why it's aggregated? Because we have a lot of training set image, right? So you see there's a big X here. So it means the image set. For all of Z given X, the aggregated posterior, we want to minimize the distance between this blue mountains with this big green mountains, and we call it a KL divergence, KL divergence. Yeah.
divergence basically tells you the difference between two distributions. Right? If you minimize the KL divergence, the two distributions should come close to each other.
Yes.
As close as possible.
Yeah, and we will see, I mean, hopefully later we will see how it's derived. But now you can see VAE actually optimized two errors. One is the reconstruction loss. The other is the KL divergence. And that's how we train VAE. And the good thing, again, introduce overlap between distributions, and also latent space will keep semantic meaning after we optimize these two laws together.
So you see, right, autoencoder was only doing reconstruction loss. Now we have reconstruction plus KL. This is the new objective. KL is Kalbeck-Leuver divergence. KL divergence, right? Which makes the mountains come under the green mountain.
Yeah.
That ensures overlap between the mountains.
And when generating the data, we directly sample only this green. Because we know these blue these aggregate posterior will match the prior. So when we want to generate new data, we directly sample from the isotropic Gaussian, which is the blue green mountain, and put it to a decoder and say, hey, decoder, decode this sample. And then it will give us a cat or realistic face, human face. Yes.
That's always Gaussian 0, 1.
Always Gaussian.
Yes.
There's no.
Yes.
Makes it easy. There's research that says, look, guys, when you match this mountain range with this one mountain, the match is not going to be great, right? Multiple mountains, you match with one mountain, the match is not going to be perfect. Okay? So what advancements now are doing is saying, why do I have to make this Gaussian? Let me learn another function which matches this mountain range very well. So instead of a Gaussian, I use a neural network to learn that function. These are called energy-based models. But what is the penalty of that? If you learn some arbitrary function that matches your mountain range very well, great. But you have to sample from that function. It is very easy to sample from a Gaussian, but sampling from that crazy function, oh, you have to go back to Markov chain, Monte Carlo, Langevin, etc. I don't want all that pain. Gaussian is good. You lose some, you gain some.
So let's say that going back to the unbalanced balance, right? So let's say I do have a balanced data set of cats, like different types of subspecies of cats, right? So then in this figure that you're showing us, they will be like two, or ideally, we have imagined that there should be two sets of mountains with no overlap in between. Because there is nothing between a cat and a dog.
Correct.
Right?
Correct.
But between the cats, there should be overlap.
Between the cats is overlap, between the dogs is overlap. Right?
Yes.
Now, and when you train this model, right, because you're starting with a cat image / dog image, you go into one of these two sets of mountains,
Correct.
and then you do a decoder.
Correct. Correct.
But then you sample it. What if you sample from the middle?
Correct.
Where
That
there is no
very
This is the big problem with VAEs.
I see.
This is called a prior hole problem. Hole because in the prior, there are some areas where the probability on the Gaussian, isotropic Gaussian is high, but on the posterior, the probability is low. It's as if there are holes in the prior.
Yeah.
Right? That will give you bad images. This is why diffusion came and said VAE is garbage, because it can give you all these bad images.
Okay, so I think I will skip this these things, but just a quick overlap. That quick overview. So autoencoder is going to do arbitrary mapping, while VAE is going to give you continuous semantically continuous overlap latent space. And to do a sample, this is training, right? So we encode into a small distribution. We sample from that, we decode, and then when doing generation, we ignore all the blue small mountains. We only directly sample from this green big mountains, and then it will give us a realistic image. Okay, so
It's already clear.
okay, sure. So just let's get into the second lens of overview, which is VAE is actually applying neural network on EM network. So we already see generator is generating posterior. Now I'm going to tell you that decoder is actually estimating this likelihood or maximizing this likelihood. So EM is saying that, hey, I want to find the color that explains that these locations and the beehive location. And what does this parameter goes? The encoder is going to learn the colors, and the decoder is going to learn the beehive locations, such that your color, your hive location together, they can explain these images the best, the rules. And that's how we related EM to VAE. We have put these slides on online. So basically, encoder is substituting the Bayes rule in EM framework. So in Bayes, we say that, hey, how do we calculate the color? It's Bayes rule, right? So now we use an encoder. Similarly, how do we calculate the maximum likelihood? We use a decoder to maximize the theta, such that given the rule, it can explain your data. Now, I want to introduce a very important idea of what actually is VAE solving in mathematics. If we look at, we are actually maximizing the likelihood, P of X, right? And then it's sample from the encoder, we sample from the posterior. Now, if we do some mathematical transformation, we multiply this log likelihood with Q phi z given x, which is your encoder output, and divide it. We can separate it into two terms. One is expectation of Q phi z given x, and this inside is pxz divided by Q phi z given x. You don't need to remember the exact term, but I'm going to tell you VAE is actually optimizing this bound, this term. Why? Because the second term is a KL divergence. And this KL divergence is a distance between two distributions that can never go negative. So if you maximize the first term, you are actually maximizing the lower bound of your likelihood. Now, if we look a little bit closer into this KL divergence, this is saying that when your encoder output latent posterior matches the God knows latent. This PZ given x is God knows the posterior. If your encoder matches the real posterior, then you will get the highest likelihood. But there's no way we can know the posterior. I give you an image. Only God knows what rule he used to create that image. There's no way we can know. So that's why we can only optimize the first term. And that summarizes my part. And then
I'll just finish up in 5 minutes. I had some other slides, but I can see you're tired. but I'll just finish up in 2 minutes. The thing I want to say is, you have my slides not complete. VAE can be thought of as bunch of forces acting on the latent space. Let's look at these forces. Force number 1. Decoder wants all these individual mountains that come from each image. Does the decoder want them to be close by or far away? Far. Why? Someone? Not please. Because reconstruction loss would be better, right? Because decoder says if I get an image of if I get a latent space value here, and that's a cat, if the next latent space value gives the dog, then it's very hard for me. Very similar input, I have to create very different images. The decoder is saying, encoder, you better put your cat distribution and dog distribution far away from each other. Then I can reconstruct well. Good. The KL divergence term. Oh, you put it over here. Okay, go next. Okay. So let me back out one more step. What is our ultimate goal? PX. PDX, right? P of data distribution. Right? And from the math, we can see that we cannot compute PDX, the data distribution. But we have a lower bound on it, and we want to maximize that lower bound. That lower bound, if you do the math, which we have skipped, consists of 3 terms. One is the reconstruction, which means the decoder has to reconstruct the cat. And then there's a KL divergence. KL divergence can be broken up into cross entropy and entropy. Okay. What is cross? So reconstruction term is clear, right? You're saying, decoder is saying, encoder, move the Gaussians far away from each other. What is that?
The reconstruction term ELBO or
No, this whole thing is ELBO.
So you already removed KL from the top.
No. So this whole thing is ELBO. The one that Wally had, sorry, the one that Yulin had, the terms inside the KL are different. I would have reorganized it in a different way, but this whole thing is ELBO. Okay. Reconstruction is decoder saying, move the Gaussians, the mountains far away from each other. Good. When you do the cross entropy is saying with that big mountain and these small mountains, they should all come together. Hey, that's contradictory. Decoder is saying make them go away, but encoder is saying, hey, there's this cross entropy term. I have to bring the mountains together. Right? You also already see the push and pull. Okay. On top of that, KL divergence can be written as cross entropy and entropy. Now, for a Gaussian distribution, what maximizes the entropy?
Should I make it flatter or should I make it sharper for maximizing entropy? Flatter. Okay. So KL divergence says cross entropy and entropy. So you're saying, hey, not only should you bring the mountains under that big mountain, you should also make these mountains flat. Okay.
Increase the variance.
Increase the variance, right? So the training objective is saying, hey, encoder, you better make the variance of each of these mountains high. Decoder is saying, hey, you better not do that. Because if you make the variance high, what will happen? The cat and dog is going to start mixing. Decoder wants the cat's distribution and the dog's distribution to be as separate from each other. These are the three forces that are playing in the latent space. And once you train, it comes to some equilibrium. And that equilibrium looks somewhat like this. There's a big mountain Gaussian, the small posterior mountains looks like this. That's what VAE is actually trying to optimize. Once you've learned, all you do is you forget all those small mountains because you've learned the rules. And now you sample from Gaussian on that rule space, you get images. What is a big problem with this? I think someone mentioned. Look, there are mountains over here. It's all under the big mountain. You cannot collapse these mountains, right? There will still be valleys over here. You agree? So now in these valleys, when you sample from this big Gaussian, those samples could come from those valleys, right? And if you decode the valley, what do you think you'll get? If you decode from the valley, right? This is a cat mountain, this is a dog mountain, this is a bird mountain. The valley is between cat and dog, it's junk. You sample from that, you get some average of cat and dog, people say, bad VAE, you hallucinated. Right? This is a major problem with VAEs, and this is called the prior hole problem. Do you have thoughts on how to solve this? How can you solve this? Steve.
The hierarchical way of VAE distribution.
You do not do this Gaussian. You make this some flexible distribution and make that flexible distribution wrap around this mountain. Right? And then you only remember that flexible distribution and you sample from it. You're never going to sample from a valley. Right? But you have to learn that distribution. That's another big problem. Okay? And there is some other problem, another problem called posterior collapse. We'll skip this for now. And then people talked about VAE is bad. People talked about VQ VAE, vector quantized VAE, which is like learning dictionaries, codebook learning. And then they went with that, and I'll finish with this picture. This is what original VAEs created, generated images. You see, right? It's reasonable. It's reasonable. In fact, papers don't report the prior whole images. So these are good images, but still, like, see the blur in the background.
Because you have to decode one sample into two similar images.
Right.
That's why it blurred.
And it realized that if I learn the rules as there are two eyes, one nose, lips, that gives me good reconstruction. If the background I try to learn, it's very hard because the background keeps changing of pictures. Right? So VAE learned these, but the backgrounds are bad. But then VQ VAE came and said, no, we are going to do something different. We didn't talk about that. But then the images became much sharper. Okay. So this is VQ VAE. Then diffusion models came and said, you babies, right? This is nothing. I can create a unicorn with a horse's tail and striped with zebra stripes, whatever I want. I'll do much, much better. And that's what we are going to go into after lunch. Questions?
What are the styles required to make such a data and model size so that we have something that looks like this?
We don't have good answers to that because we don't have great experience on what the model architecture should be and what the size should be.
So it really, it really depends on what you want to model. So a famous set is called, for example, CFAR, which is like your hand strokes that of digits, 0, 1, 2, 3, handwritten digits, right? And in that kind of simple image, because you only need to predict digits or reconstruct digits, then maybe you only need like 10,000 images in this kind of size to train good models. But if you want to model some good pictures like what you can ask today's ChatGPT, say generate a new human face wearing some very good clothes, then maybe you need a mega, giga, this kind of set of image size and real model size. Like it all depends on your dimensions.
So when you generate images, is there any better strategy than doing random sample? Because random sample does not give any information.
Yeah, so for all these, like in VAE or later generative model, most of the generative models, you can always conditional on prompt. So the way of conditional it on prompt, I will say quickly, is before you put, when you are training, you always put only image to the encoder. And then if you have some label of this image, you can also feed it as also to the encoder. So in your latent space, there will be some information, some dimensions that's on your classes label and so on. So later you can only condition on these latent spaces or dimensions that you will give you some direction saying I only want cats or like I only want brown cats. Yeah, these kind of.
Let me understand your question a little bit more. Why do you say random samples don't have information?
Random sample is like it does not give any hint about what kind of.
But you see, right? I trained the latent space to match the isotropic Gaussian distribution. So when I sample from the isotropic Gaussian, actually my latent space is very meaningful. All the cats and dogs have come and sat underneath the isotropic Gaussian, right? And so
If you sample far away from the Gaussian, if you sample here, those are all junk images. But all the realistic images, they have come and mapped over here, right? So it's not that sampling from that isotropic Gaussian means all junk, right? There are some regions that you cannot avoid because you cannot collapse the two mountains into one mountain.